Engineering at Ohio State, and Dr. Alton also serves as Director of the Engineering Research Center for Net Shape Manufacturing and the Center for Precision Forming at Ohio State. This year, Dr. Alton also has published a 2-volume book on sheet metal forming, fundamentals and applications, which addresses this topic and is available from ASM International. Today, Dr. Alton kicks off our 3-part webinar series with a presentation titled Servo Press Technology, Applications for Today and Tomorrow. Please welcome Dr. Tylen Alton.
Can I start now with the next slides?
Yep, go ahead, Doctor.
Okay, so here is the title. I don't have to elaborate on that. I just would like to point out that the websites, if you want to have more information about the activities of our group, you can go to the website, and there's a lot of information on sheet metal forming, especially www.ercnsm.org. Slides are numbered, and I mentioned the slide, of course, number 3 now. This is the approximate outline of the presentation. And since I really don't know the background of the people who are listening or watching this presentation, please feel free to submit your questions. That will give me a feel what to emphasize more. And if I don't know how to answer your questions, then I will tell you I don't know, and I will respond to you later by email. So I'm going to slide 4, which is really the key point in understanding the capabilities of a servo press. So what you see here with the blue line is a typical slide versus time curve of a mechanical press, which is like a sine curve, sinus curve. And the red one is supposed to schematically illustrate the motion curve of a servo press. So what are the capabilities of this machine? Number 1, you can change the stroke length. So it's not like a mechanical press where you have to go top dead center and bottom dead center. So you can change it, this stroke. Number 2, which is very important, but it's not widely used, is you can adjust the speed of the ram during the formation. In other words, you can come during the entire stroke. You can come very fast and go very slowly. And number 3, you can dwell at the bottom if you think that part requires that. And you can also do some pendulum effect. In other words, after you pass the bottom dead center, you can go back right away and go backwards, which you cannot obviously do with other mechanical presses. So you can do it with hydraulic presses, but you cannot do the mechanical presses. And then number 4, as indicated in the slide, you can do other processes. You can do assembly, you can do maybe welding at the same time in the same press during the same stroke, if that appears to be effective or useful. Number 5, by adjusting the speed of the ram, you can avoid shock, because you can touch the sheet metal very softly, and also you can reduce the reverse loading, which is an important issue during blanking. And finally, number 6, if you are doing a transfer press operation, and we will get into this a little bit later, you synchronize the motion of the press with the feeder, with the automatic feeder. You can even bring the press, slow it down, the ram, I mean, slow it down or stop until the part is transferred automatically. So I'm going now to slide number 5, which is really a summary of what I discussed, but let's go through them very quickly. So the fact that you can control the ram position and velocity very precisely, that also allows you to do easier setup when you are the first setting up the ties. You can adjust the stroke length, top dead center and bottom dead center. And as I mentioned, ram position velocity can be synchronized with the automatic part transfer. And we'll see this later in deep drawing. Cycle times can be shorter than in mechanical presses because you can move very fast and then slow down, just like you do in link presses, but this is more in controlled fashion. And you can save energy because you don't have a flywheel that is continuously running. And you can have, of course, dwell, as I mentioned before, and you can, in some cases, even use variable blank-holder force and vibrate the die or the blank-holder force, but that's not a very major application. And then the motor torque is available during the entire stroke. Now I'm going to slide number 6, just to give you a little bit of perspective and history, because I have been interested in Servo-Drive presses for maybe over 10, 15 years, and I saw them first in Japan, and the initial servo presses were small, and they use low torque, high RPM motors, and they have to have some kind of a linkage mechanism to increase the force and torque capability. But lately, in the last maybe 7, 8 years, people developed high torque and low RPM motors that can be attached to press structure without any linkage mechanisms, and these are really that open a whole new capability in servo press applications. You see in slide 7 the old design. You see the small servo motors, high RPM, and with a timing belt you can change the RPM, of course, and then you have a ball screw system. But as you can imagine, a system like this may have maintenance problems in the long run. Slide 8 shows another design of the servo presses, what people were trying to do. In this case, you have 2 small servos with a linkage mechanism that drives a slide down, and this linkage mechanism, of course, increases the force capability of the ram, and also takes care of any eccentric load you might have. As I said, these are old designs. New designs for larger presses are entirely different. I'm going to slide number 9. This is, again, one of the C-frame type servo press that I happen to work with. And what you see here is the mechanical design of the C-type press was not changed. The only thing was changed, instead of a flywheel, a servo motor with a capacitor as a power source was attached to the press. This, in my view, that was a very good idea, because the press building companies, press companies, did not have to change the design of the structure of their presses. Obviously, that made it better for them, and also people are accustomed to existing press structure, so it was good for the builder as well as for the user. And what you see on the right of this slide, number 9, an example stroke time program that shows how the servo press can be programmed any way you want. But in this case, it was programmed so that we had from 1 to 2 rapid approach, 2 to 3 dwell, and then further down from 3 to 4, and then rapid upstroke. This was for warm forming aluminum magnesium sheet, and I will show you some examples. But these are, of course, not mainstream applications, but when we were doing research and development, we used this kind of press characteristics. In slide 10, you see today's servo press applications. These are large torque, large motors attached to the structure of the presses. Basically, again, you remove the flywheel, and you have servo motors that drive the gears, but the rest of the press structure is essentially the same. And I happen to take this from one manufacturer, but other manufacturers are using the same design capability as well. So the fact that we have now high torque, low RPM motors available makes it the whole design of the press. You can build larger presses, and we will see that up to 2,500, 3,000 tons presses for automotive OEMs, and also the small presses are easily designed and constructed. Now, on page 11, I thought I mentioned this. You can see the sketch of another design. This is from a company called ABB from Sweden. And what you see here is basically you have a mechanical press. In addition is a servo motor. This is the green on the right side that can drive the gear that is already driven by the flywheel and the drive shaft. And the reason for this is that you can adjust the speed of the slide by releasing the clutch that you see on the left side and by activating the servo motor to change the speed of the slide. So I have seen some examples in Europe especially that some people added this hybrid servo press design to their existing mechanical press. So this is just as information. And this so-called hybrid servo press looks schematically as you see in slide 12. Again, you have the flywheel, but in addition you have a servo motor, and when you clutch disengages, then the servo motor drives the rest of the ram. To give you an idea about what is happening around the world, by the way, I should add at this point that there are really three, in my view, as somebody who's working with sheet metal R&D, three major developments going on in sheet metal forming technology. One is advances in advanced high-strength steels to save weight and improve crash resistance, of course. Number two, the technology that's called hot stamping. You may have heard about it, where a certain alloy steel is hot formed and then quenched in the die, and you can obtain very high strengths up to 1500 megapascal. And the third development, in my view, is servo presses, and a lot of people expect that servo press technology is going to revolutionize sheet metal forming, but of course that's not going to happen right away. It's going to take many years, but most people who make new investments, before they make it on mechanical presses, they kind of look at servo presses and say, am I getting, even though they are a little bit expensive, the servo presses, am I getting capabilities that I can use better for my business? In this slide 13, you see some of the presses that have been installed or being installed in Germany. You know, as you can imagine, German companies are using Schuler. That's their major press supplier. In Japan, there is Komatsu and Aida, and I have some examples here. I'm sure Komatsu people are going to talk about this in the next webinar, but I have some examples of Aida I happen to know, and Honda in the United States has already two Aida 2,500 ton presses, and the stroke rate is about 17, 18 strokes per minute, which is quite a bit larger than comparable mechanical transfer presses for the same size dies, which is about 12 strokes a minute. So, so you can see from this slide a little bit what's going on around the world, although I don't have all the information, of course. Slide 14 shows a schematic of the Honda Suzuka press. That is the first station is the dip throw station. These are tandem lines. One of the reasons people use tandem lines is that first you can adjust the speed of the ram on each press independently, and especially if you start forming high-strength alloys, then in a transfer press, in the first station you have a larger force, then you have a tilting of the ram. And if you have a tandem line, then this tilting is, of course, doesn't exist because you have different rams for different stations. So you can obtain, as you see in this slide, a better formability, and you can increase the productivity. I will show you some examples of it, what I mean by that. And also, very important in Europe and Japan is the energy saving. Of course, energy saving is important everywhere, but obviously if the kilowatt hours or gallons of gas is 3 times as much as in the United States, then energy savings becomes even more important in Japan and Europe. Next slide, 15, you see a comparable press. I think this is at BMW Leipzig plant. Again, a tandem press line by Schuler, and you can see the capabilities, not capabilities, but specifications of the press approximately. And here is the Aida press that is in Japan, as well as also one in Ohio. I have in fact visited it just a couple of days ago. It started production, and Honda is going to put another one in Alabama. Now, I am on slide 17, and what this slide shows, number one is the gray line, which is the stroke versus time of a mechanical press. By the way, these are actual numbers that I received from Schuler, 1,100-ton mechanical and servo-drive presses comparable. And the red line shows how the stroke in the servo press, the stroke rate or the velocity of the ram is larger, because the slope of the curve you see is the velocity. So what is interesting in this slide is that the deformation speed is the same whether you use the servo or whether you use the mechanical press, but because the servo can move up, well, the ram can come down, downstroke faster and upstroke faster, you can decrease the cycle time. So as a result, you can make 19 parts per minute in this press, comparable parts, similar parts, versus 14 parts in the mechanical press of the same capacity. So that's what I mean by productivity. Because of the slide velocity, you can change as you wish in a servo press, and this is all servo presses have the same capability. Now, what you see in slide 18 is that you can reduce the stroke length, or you can also work in pendulum mode. As a result, you don't need all the time to go to the top dead center like in a mechanical press. As a result, the cycle time can be reduced drastically, in this case 100%, and as a result, of course, you have increased productivity. But this is the case when you need flexibility in your shop, and sometimes you need large strokes, and then sometimes you need small strokes. So that capability and flexibility also exists. Now, in slide 19, we see another application. Again, the gray one is the slide stroke versus time, and the red one is the servo press. In this case, we slowed down the servo press. Sorry about that, something came here. Okay, we slow down the servo press. Again, as you see, the red line, the slope during the formation, because the part required slower process. There are some parts that if you, and I will talk about that, when you slow down the speed during the formation, you can get better formability. And there's a reason for that we will discuss. So in this case, even though you are reducing the speed of the formation, during the deformation, speed of the ram during the deformation, you still get larger productivity. So that shows the some of the productivity advantages of the servo press of comparable size. Slide 20, I took that from a paper published by Honda people in Japan when they installed the first Aida press, and they were using it for side panels. And they claim that in the mechanical press of the comparable size, comparable bed size, they were having crack problems. Of course, there are ways of reducing these problems, but with the servo press, because of the speed adjustment and some of the proprietary developments they made, they are reducing the crack formation. In this case, they eliminated it. But this is a problem I guess everybody's facing in the sheet metal industry, especially when you start making, forming harder to form materials like advanced high-strength steels or harder aluminum alloys, and then these difficulties always come up, and everybody has their own tricks and die designs and cushion controls, etc., to avoid these problems, or at least to reduce them. But obviously, if you can reduce the crack formation and you can reduce the scrap rate, that could be a tremendous advantage. And I will go quickly. I am now on slide 21. Some examples. This I have taken it from Mr. Miyoshi Komatsu, engineer. And what you see here, that by changing the speed of the RAM during blanking operation, and you can precisely control it, precisely meaning in terms of 10 microns or so or less. So as a result, what they did here, we see on the left side, the slide position, they penetrated the material, but they did not entirely go through it. They came back and they went again. So as a result, they claim that the finished blank had better edges, similar to, not quite as good as in fine blanking. So that is, of course, very, very good advantage. Now, we have to remember that during the, I'm sure you guys all know this, during the deformation, there's elastic deflection of tooling and the press. So when you do these double motions, some of that elastic deflection is eliminated because the forces you apply in the second phase of the stroke or slide motion does not deflect the tooling as much. So that is one of the issues, that very fine difference that you can obtain with the servo press applications, especially in blanking. Slide 22 shows another example. This was a special alloy, specific applications, so-called shape memory alloy. I think they were making some eyeglass frames with this, and through multiple motion, you see the slide motion on the right, they were able to, excuse me, they were able to reduce considerably spring back. This is one of the issues, in fact, that by using the so-called pendulum motion, that is to say, the slide passes the bottom dead center, but immediately comes back to coin or form the material once more. At that time, there's a possibility of reducing spring back. Spring back, as you know, is a big issue with advanced high-strength steels. As the strength of the steel increases, spring back issues increase, and you have to do all sorts of die design issues, die design tricks to be able to reduce the spring back. Or if you do computer simulation, you have to predict the spring back and then modify the geometry of the dies accordingly. That's the current practice today, but several presses may add to the solution of this problem. Again, slide 23 shows another example. I don't have to say much about that. This is the, again, adjusting the speed allows some ironing of the pierced hole, and you can obtain better quality holes by this technique. Slide 24 is another example. Again, by running it slowly, it is possible sometimes to draw slightly harder materials, and because you might ask, why does it make, why is the speed so important? During the formation, you generate heat because the mechanical energy you put into the formation turns into heat, and this heat is especially important at the interface between the die and the material, and that affects the lubrication. So unless you have some pressure additives, which usually you do, and temperature additives, that makes the lubricant pretty effective, you may have problems because of high speed during friction because line interface temperature is high. I got a problem here now. I cannot go. Brad, are you there?
I am here.
I cannot further with my slides for some reason. I don't know what happened. Okay, do you have the control? Can you pass the control to me again?
Yeah, Marlene, are you there?
Yes, I'll take it to myself and then back to you.
Yeah, something happened here. I cannot move the slides further. I am at slide 24. Marlene O'Brien was presenter. You're no longer present. Okay, I say okay. Show my screen. Okay, I'm going there. I go to Microsoft PowerPoint. I should be okay now. All right, I am going back. Okay, I am all set. Thank you.
Good.
Slide number 25. Again, this is another example where you stop the press at the bottom or near the bottom dead center, after the bottom dead center, and then you can make another operation like staking or assembly of a part. This is just an example. It may or may not be cost effective to do this, but in some cases it may be. Now, slide 26, we have seen it before, and I have put this here again because I want to show you some of the work we have done very briefly on warm forming of aluminum, titanium, magnesium, and stainless steel. What we have done in this case is that what you see in slide 27, you have aluminum alloy 57 and 54. We formed this cup. It was a 40-millimeter cup just to laboratory experimentation, and we could increase the LDR, which is the limiting draw ratio. That is to say, the ratio of the initial blank to the diameter of the initial blank to the diameter of the cup. We could increase that 2.9 using increasing temperature of the aluminum alloy, and this was done by Duell and heated dyes that heated the material. Now, this is a kind of unusual application. I'm not suggesting that you should do it, but people are looking also in the possibility of warm forming aluminum alloys with using heated or not heated dyes. And here is the on the right side another alloy 5052. Again, 275 degrees centigrade for this alloy gives higher LDR limiting draw ratio. We did the same thing with magnesium. I don't expect that many people form magnesium, but for a while magnesium was very exciting because it's lightweight and high strength, but forming is very, very difficult. Titanium, you see on the right, there are some people who make titanium parts, especially for pacemakers. For example, in that case, forming titanium at an elevated temperature gives quite good results, and in this case, the application of several presses also, at least in our studies, showed advantages. And finally, as far as warm forming is concerned, I show you an industrial application. I must admit I don't know whether it's just being done still, but it was done 5 years ago. That was the laptop cover for the Sony laptop, a process developed by Aida and Sony for forming magnesium laptop case using a servo press. And on the left side, you see how the slide speed and slide motion was arranged. It was coming very fast, slowing down well, and then continuing the forming because magnesium had to be heated in this case. Otherwise, you cannot form magnesium. It's very, very brittle. Now, one of the things I should also mention here is that the cushion. Cushion is a very important issue, obviously, especially in large parts for controlling metal flow. And what you see here on slide 30 is, in my view, one of the best designs I have ever seen, although probably one of the most expensive cushions ever. This cushion is already in operation in Honda plants and in Japan as well as in the United States. What you see here is, as you see from the sketch, it's a servo motor, and the blank holder, you see it there as marked die, the upper die. The cushion pins are holding the blank holder, and this slide shows only half of the press. So you see 2 hydraulic cylinders in the bottom, but normally you have 4. And what this cushion does, in addition to arranging for pre-acceleration and changing the force, cushion force during the stroke, it uses the cushion hydraulic pressure during the deformation through the hydraulic motors that you see in the bottom, and the servo motors are working as generators, and it generates electricity. In other words, in a hydraulic cushion today, when you press against the cushion, the energy that the cushion absorbs is generated, causes heat up in the oil, and then you have cooling systems to cool the oil. But in this case, the oil pressure under the cushion is used to generate power and save electricity. The next slide, I don't have a number on it, should be 31. The capabilities of the self-driven hydraulic surface cushion. Some of you may be familiar with this. As people start forming advanced high-strength steels or more difficult to form alloys, hydraulic cushions become very important, and they have the capability of pre-acceleration. In other words, you can also use these cushions in mechanical presses. Before the ram touches the part, you move the cushion slightly in the blank holder so that the touching is soft. It's not a shock type hitting on the blank, so the lubrication is better, and you also protect the press and the tooling. The cushion item 2 here has capabilities to change the pressure and the force during the stroke. That also helps to make the material flow better. And then, of course, you can control the return of the cushion pins so that you don't have to kick out the part immediately. So because you have a flexibility, you have the flexibility of controlling the cushion as you wish. The next slide, 32, shows you the schematic of the cushion I was just describing. As you see, is the hydraulic cylinders in the bottom send the pressure to, there's an accumulator where the oil is. Of course, all the system is closed. And during the downstroke, when the cushion is pushed down, the yellow oil goes into a hydraulic motor. The hydraulic motor drives the servo motor that generates power. And Honda and Aida claim that in their Suzuka plant, Honda Suzuka plant in Japan, in their operation, they are saving approximately 70% of the cushion energy, again, to drive the press. Now, I'm coming to the end of this presentation. Just let me try to summarize some of the, at least in my perception, some of you may not agree with this, but what are the major challenges in forming first advanced high-strength steel? This is a big issue for Tier 1 and maybe some Tier 2 suppliers, and also some OEMs also are trying to explore whether they should do advanced high-strength steel. These are dual-phase DP trip steels in-house. Obviously, the challenges are these materials have low formability, and the fracture is more possible, and there may be variations from mechanical properties from batch to batch. According to my experience and my discussions with many industry people, this is a major problem in high-strength steels. Of course, the forces are high, so sheet die interface pressure and temperature is high. So that is one of the reasons why we slow down the press during the formation. Of course, the strength being large, that also affects the tool wear, and in blanking, large reverse tonnage, and large spring back. These are big issues in the advanced high-strength steel forming, and I'm sure that those of you who are doing this are probably facing these problems every day. Now, what can the precise ram position and dwell and velocity control can do? Number one, allows for easier die setup. Some people really say, this is great. We can set up the dies much easier. And, of course, it prevents noise and shock. We discussed that already. And improves the formability and reduces fracture by reducing ram velocity during the formation, especially during the drawing stage or stretching or bending stage. And that also improves the lubrication. And of course, as I mentioned before, reduces shock loading and reverse tonnage and blanking. But I must say that all this information is really anecdotal. There is no research, at least to my knowledge, quantifiable in the public domain that one can say, oh, that's what I have to do for such and such material or such and such part by reducing the ram speed to such and such level. So that kind of information, unfortunately, everybody develops through trial and error themselves, and there is no, to my knowledge, any research, neither in the United States nor in Europe. There may be some Japan, maybe I cannot read all their publications, but there is definitely not in Germany either, although they do a lot of work on metal forming. So there is a need for really developing this technology. Slide 35. What does dwell at bottom dead center and pendulum motion allows? If you do the pendulum motion, which is the ram goes up, passes the bottom dead center, and quickly comes back, then before the material fully strain hardens, you can reduce spring back. There's some anecdotal information on this, but nobody knows exactly the details and the scientific explanation for this. Obviously, number 4, when you change the stroke length, that provides flexibility, and you can, according to the part and dies, you can use the same press for drawing as well as for blanking, for example. And then, of course, again, I am repeating and summarizing what I discussed before. Ram position velocity can be synchronized with automatic transfer if you are doing automatic operation, and the speed can be adjusted during the deformation. So, in summary, the technology is here. In fact, small presses are used by many, maybe some of you, I would imagine many of you are already using it. And it started in Japan, but it is now in this country accepted, also in Europe. And now large presses are built also, and that's the big issue. Every time the OEMs or first-tier suppliers have to change some press line or old press line, they look at the servo presses very carefully. They say, maybe even though it's a little bit more expensive, maybe we should invest our money in this. And direct drive motors, energy recovering cushions are used. Transfer presses are installed in various OEMs and first-tier suppliers. I don't have all the list, but these are just information that I gathered by talking to people. And one of the issues is that if you can develop new tool designs, maybe multiple motion tools, and maybe assemble in the same press for small parts, for example, that also can bring some advantages. And of course, Servo-Drive presses will definitely contribute to improving the technology for forming advanced high-strength steel and aluminum alloys, no question about that, but we don't know exactly the scientific and technical rules for that yet. So slide 38 is finally my final slide, and you have my email, my phone number, and also I gave you the reference that Brad mentioned, the book that it just came out this August. So if you're interested knowing more about this, you can contact me, you can contact Brad or whatever. So I stop here, and then we still have 15 minutes or so. If there are any questions or comments, or if you don't agree with what I'm saying, that's fine. You know, I am open to constructive criticism or any suggestions you want to make or any new information you want to throw on the table. I would be happy to listen and try to respond the best I can. Brad, is that okay?
That's wonderful. Great job. Yes, we've got about 15 minutes left for questions. There's a lot of people attending today's webinar, so we'll do our best to address all of the questions. The first two questions are related to the PowerPoint and when they can get a copy. We will post the PowerPoint to the website of Metal Forming Magazine within the next day or two. Actually, the entire webinar recording will be posted to the website. Anybody wants the slides, they can get in touch with me at bkuven@pma.org, or Dr. Alton had his email address up there as well, and he can send you the slides as well. But the entire recorded event will be on our website, metalformingmagazine.com, within the next day or two. Whoops,
So are there any questions? I'm sorry.
Yep. One of the questions we have, if converting from traditional mechanical press to a servo, how does the motor sizing compare from the AC to the servo? Don't you lose energy when you displace the flywheel?
I presume this question is related to the hybrid design?
Yeah, it seems that way, yep.
Frankly, I really don't know, because if the person who's asking the question, if you send me an email, I can send you the papers and the contact names from ABB. They would know that better. I don't remember. I read the paper, but it has been a long time ago. I don't remember how they figured this out. I presume they look at their mechanical press, and based on the size of the press and the drive of the press, they make a proposal to you saying that you have to have such and such servo motor and such and such gearbox, and that's how much it's going to cost you, I presume. But I really don't know. I cannot answer that question, because this is something really the servo motor and the hybrid servo press manufacturer would know.
Okay. And your email address, again, I know you switched slides, but you want to tell people what the email address is?
I go to the last slide. Okay. Maybe that's better than me saying it. Okay, here we go. alton.1@osu.edu.
Okay, easy enough. All right. Do you know how many inch tons of force some of these presses can generate? Inch tons.
The presses go anywhere from 20 tons to up to 3,000 tons. You know, the servo presses.
Right.
So the 3,000-ton presses are, of course, for the OEMs for forming very large parts, and the smaller presses are for, I guess, small companies doing various parts. But I think most of them are used in the range of maybe 200 to 600 tons or so.
Okay.
That's my information that talking to people.
Okay. Can you address the complexity in programming servo presses compared to a typical press? And before you answer that, let me say that we are going to address that topic in the future webinars next Thursday and the Thursday after that. We'll talk a little bit about some of the controls advancements that are going on to impact the programmability of servo presses. But do you want to comment at all on how?
Well, from what I have seen, the programming of the press per se and setting up the speeds and so on, that's relatively easy because I would imagine with very small training you can learn, because usually it is a bunch of points that you select, and then each point is assigned a velocity. But this is all automated. At least I have seen it for Aida presses, and they are very, very easy to do. What is not so easy is one has to learn a little bit about the control issues of the press, the maintenance and service issues, although obviously the press manufacturers, I am sure they have done anything they can. But I remember listening to a presentation by Honda people about the details of the large presses. So there's a lot to be learned in operating the press, especially maintaining it. Operating is not a big issue, but maintaining it requires a little bit of learning because they are using obviously different controls than mechanical presses.
Right.
But in mechanical presses, you have to learn about maintenance issue as well. So I am not able to answer that. Again, this is every manufacturer has their own maintenance and training programs, which is provided once you decide to buy a press or you show interest. I'm sure they explain that everything.
Right. Next question is, what is the energy balance differential between an AC motor and a servo motor on a similar forming application? And you know, he says energy balance, but maybe he means you know, that the energy savings or the energy consumption for like applications between servo and AC. I'm assuming that's what he's saying. It's not.
I think in terms of energy consumption for a given torque, there is not much change. I mean, that's very similar. But the issue is that when you have a mechanical press, you're running the flywheel continuously. Okay? Even though you are not extracting energy from the flywheel, you still have to run it. And the servo-drive press, you're using the servo press, the servo motor, only when you're doing the deformation and moving the slide. So the energy savings mostly, I believe, comes from the cushion. Because the cushion energy, which is usually hydraulic cushion energy, is lost as heat. In this case, is recovered. At least not entirely, but they claim 70%, it may be 50%, I'm not sure. But, you know, you have to look at it this way. The mechanical energy, that is force versus displacement, and the integral under that curve, that is decided by the process. So the process takes a certain amount of energy. Now, the question is, how efficiently is the energy provided by the machine to the process? And in the servo-drive press, it's a little bit more efficient because you only operate it, you only activate the motor, the servo motor, when you activate the slide and the deformation.
Right.
I don't know whether I am able to answer that properly because it will be better to have this face-to-face probably, but at least that's my take on it.
Yep. Okay. Is there a sweet spot in terms of tonnage for the servo-driven hydraulic presses, cost versus performance that you've seen? He says servo-drive hydraulic presses, and I'm not sure that's what he means.
Well, you see, when we say servo presses, sometimes hydraulics are also called servo presses, you know, because
yep.
The word servo implies that you have a feedback mechanism in the motion. So there are some people say, well, I have a servo hydraulic press, right? And that means that they have several valves to guide the motion of the hydraulic press. That's not what we are talking about it now here.
Right, right.
We are talking about a servo motor that moves, rotates with pulses. In other words, according to how many pulses I give to the motor, it rotates so many degrees, and because I know exactly how much it rotates, anything attached to the end of it rotates also proportionally about the motion of the motor, rotational motion of the motor. This is entirely different from hydraulic servo systems that are basically servo valves try to adjust the best they can the flow of the oil to the ram or to the cushion. So it's not the same thing. I think we should not confuse that, even though the word servo comes in both.
Right. Let's say he meant servo-mechanical. I'm not sure that's what he meant, but in the case of servo-mechanical presses, have you experienced that sweet spot, cost versus performance in terms of tonnage? I'm sure that's based on the applications, right? So
I have some anecdotal information, which again depends on the supplier or on the press manufacturer. I think in general, comparable servo press and mechanical press, servo-drive press, I should say, mechanical press, the servo-drive press is 20–30% more expensive, I believe. But this is again rough numbers. If you talk to somebody like Komatsu or Aida, they can give you exact numbers because they sell both.
Right.
So, but there's no question about it that servo-drive presses are more expensive. I mean, that's a fact. Right. Our question is 20% or 30% or 40%. I guess it depends on how many bells and whistles you're going to have.
Right, and the type of work that you can do. I mean, as you've shown here, you can do different types of work on a servo than you can do on a traditional mechanical.
I think what is necessary maybe is that people, what they do is they try to learn about the servo presses by talking to the manufacturers, by if they can, visiting other companies, but that usually is not possible, to try to learn what capabilities the presses have, and then they say, hey, is that appropriate for my operations? Because right. Look, if you're doing an operation that is always the same and you expect to do the same for the next 3–4 years, and everything is working okay, you don't have any problems, then you're not going to pay another 20–30%, even if you want to change your press for the servo press. Again, you only buy the servo press, I believe, unless you have a new order, you're going to expand your operations, or you have a press line, old presses that you want to change, the maintenance costs are too high, so then you're looking for a new press. Then you have to make a decision. Am I buying a press maybe more modern but similar to the presses I have, or should I try to look into servo presses? And then it becomes an examination of what kind of parts I make, what kind of parts I'm expecting in the future. Am I going to make difficult to form parts, and so on. So then obviously not always an easy decision, but those considerations would enter into the decision, I believe.
Yeah. How repeatable and accurate do you believe that the servo press is in hitting bottom dead center?
Oh, it's in microns.
Yeah.
I mean, it's extremely accurate. And again, you can test this because, of course, manufacturers give you some specifications, but I usually don't take that as a word. You can run some tests by putting a sensor and measuring the distance between, let's say, from a flat plate and the bottom dead center of the RAM. But this measurement has to be made under load, because if you do it under idle, then it's just easy. In other words, if you don't have any load. If you have the load, then the press is going to deflect slightly. Everybody knows, I'm sure. And you have to make adjustments on the pressed RAM bottom dead center, and you can do that easily on the servo press. But repeatability, from what I read, what I have seen, talked to people, is extremely good in the micron range.
Right.
It depends on the size, of course. I'm talking about maybe small presses, but in large presses, I don't know, but I'm sure they are as precise, and more precise than mechanical presses.
And along those lines, then, have you seen the advantage of servo presses for coining operations?
Yes. Because in coining especially, I could do what they call a pendulum motion. In other words, I could come down, coin it, a little bit and go past the bottom of the center and come back right away and coin it once more. Okay? Now what happens then, in the second operation, the elastic deflection of the press will be less. You cannot do this in mechanical press, obviously.
Right.
And you can obtain slightly more precise coining operation. So I would think that, I believe from what I read and what I know, but again, I'm not a guy who's doing these things every day, so I would suggest that anybody who's interested in this and was thinking about seriously about buying press, they would go to one of the suppliers and say, look, this is what I want to coin, run it for me and see what kind of precision you get. You know what I mean?
Yep. Yep. In terms of energy efficiency, somebody says that they've heard that the average efficiency gain versus traditional mechanical press is 30 to 40% with servo. Is that kind of in line with what you've seen? I think you did say that in your presentation at some point.
Well, there is no question about it. There is an energy savings, but whether it's 30 to 40%, I don't know, because it depends on the press size. You know what I mean?
Yep.
Flywheel size and so on.
Right.
Now, I know that you have a lot of energy savings with the cushion, but that's a different ballgame. You know what I mean?
Right.
Because you are using the cushion pressure to generate energy. But I don't know, 20, 30% definitely looks reasonable. In the large presses, it might be even larger.
And does that account for the energy that's lost starting and stopping? You know, you said that since you don't have a flywheel, that's, you know,
that's right. I mean,
continuously. But you're starting and stopping the inertia of the press. So.
Absolutely, absolutely. Because you have to get the flywheel. Again, how you operate. You know, if you're operating continuously, you know, you did the setup, and once you did setup and you're operating continuously, the flywheel rotates, and then you clutch in and out. You know, in the mechanical press operation.
Right.
But if you are that takes energy. I mean, you lose a lot of heat and energy in the clutch, in the brake.
Right.
The servo press, the brake, you only use it to secure that it's safe. Otherwise, the motor itself starts and stops. So you don't have the heavy inertia of the flywheel that you have to also. And if clutch, if the flywheel is running continuously and you're clutching in and out, then you lose some heat on the clutching, which you don't have in the servo press.
Right.
The 20 to 30% energy savings in the servo press, even with the cushion, I think that's not unreasonable, but depends on the press size, of course.
Okay. We're going to take one last question, and then we'll have to wrap things up. Your email address, again, is on the screen if people want to address you with further questions down the road. Last question is, how does a servo press protect itself? And the various manufacturers are going to offer different ways of overload protection. What have you seen in terms of overload protection?
Well, I am hesitating to answer that because I know that, for example, on one presses, on Aida, there's an overload protection, and also in their mechanical presses. Now, in the servo press, the overload should be easier to do, but I really don't know electrically. In other words, if the load is higher than a certain level, then the motor just turns off. So
yeah.
That could be. But I am at this point, I really don't know for sure.
Okay.
I know
and
that.
I want to remind. Yeah, go ahead.
Yeah, go ahead. I know for sure that you have mechanical overload capabilities in most presses, but whether you need the same thing in the servo presses, I'm not 100% sure.
Yeah. Okay, great. Well, again, I want to thank Dr. Alton for launching our webinar series. Again, the next webinar in our series is next Thursday, August 30th from 2 to 3. And we will have Jim Landowski from Komatsu on the line, and he can maybe address some of these more specific press-related questions. That webinar is focused on applications such as drawing difficult-to-form materials, which Dr. Alton touched on today. And then the last webinar on September 6th, we'll talk about some of the technologies that are supporting servo press applications, specifically controls and feeds. Again, I want to thank our sponsors for this series of webinars so that we can bring these to you at no cost. They are Sei, Komatsu, Code, Dallas, Winters, and Voith. Thanks again for attending the program. We hope you found it valuable. And remember that it will be archived on our website within the next couple days, metalformingmagazine.com. So you can review it.
I want to thank everybody, too, for the questions, because I will find out certain answers for the questions that I didn't know. I really appreciate the questions.
Great, thank you. All right, so I look forward to everyone attending next Thursday. If you've not signed up for that yet, you can do that on our website as well. You can close your browser now. Have a great afternoon, everybody.